Every kernel we wrote so far ran correctly, but correct is not the same as fast. Most kernels are memory bound. Their speed is set by how quickly bytes arrive, not by how much math the chip can do. So this part is about moving less data faster. Welcome to Part 5, the memory hierarchy. In Part 1, we drew the roofline and found a kernel sitting far to the left. It was spending more time waiting on memory than computing. Most kernels live there. So from here on, the goal is moving less data faster. Back in Part 1, we drew the roofline. A plain kernel sits far to the left on that chart. That means it is memory bound. Its speed is set by how fast bytes arrive, not by how fast the chip can compute. So the rest of this unit answers one question: how do you move less data faster? First, why memory is the bottleneck. That is the roofline callback being memory bound. Second, the memory hierarchy. Registers, shared memory, L1 and L2 cache, and global VRAM. Third, global memory coalescing, contiguous reads against scattered reads. Fourth, shared memory banks and the barrier, a scratchpad __ sync threads in 32 banks. And fifth, constant memory in the labs, the broadcast, then you predict on paper. This is the same chart from Part 1. Our vectorad kernel still sits far to the left, under the bandwidth diagonal. The bottom axis is flops per byte. The diagonal rises from the origin up to a ridge point, then a flat ceiling runs across the top. That red dot, vector add, sits deep in the memory-bound region, far below the ceiling. This diagonal is what the rest of the unit climbs. Every trick from here on pushes that dot up toward it. A memory-bound kernel lives under the diagonal. The rest of this unit is about climbing it. A common wrong instinct is guessing a kernel's speed from how many threads it launches. Thread count says nothing about whether a kernel is memory-bound. What decides its speed is how many bytes it moves per useful flop. Two kernels with the same thread count can differ hugely in speed if one moves far more data. Let's recap. Most kernels are memory-bound, limited by how fast bytes arrive. The roofline shows it. Low intensity sits under the bandwidth diagonal. Everything from here to the end of the unit answers one question: how do you move less data faster? The GPU does not give you one memory. It gives you a hierarchy of tiers, each with its own speed and its own scope. Knowing which one your data sits in matters most. Let's build that picture from the top down. The GPU does not have one memory. It has a hierarchy, several tiers, each with a different speed and a different scope. The higher you go in the hierarchy, the faster it gets and the narrower its scope. Registers belong to one thread and shared memory belongs to one block. The lower you go, the slower it gets and the wider its scope. Knowing which one you are touching is what matters most. We'll build this pyramid from the top down, fastest with the narrowest scope first, slowest with the widest scope last. At the top, registers. They belong to a single thread, and they are the fastest place to keep a value. Next, two tiers that share the same on-chip SRAM, the fast static memory built right into the chip. Shared memory is per block, and you manage it by hand. L1 cache is per SM, and the hardware fills it automatically. Below that, L2 cache. It belongs to the whole GPU, and every SM shares it. At the base, global memory, also called VRAM. It belongs to the whole GPU, and it is the slowest tier with the widest scope. On the NVIDIA L4 we use in this course, That memory is GDDR6, a kind of graphics memory. Chips like the 100 or H100 use HBM instead, which is short for high bandwidth memory. Registers, then shared memory or L1, then L2, then global. Each step down is slower but wider in scope. Shared memory and L1 sit on the exact same physical on-chip SRAM, but they are still two different things. Shared memory is per block, and you decide what goes into it. L1 is a per SRAM cache that the hardware fills and evicts on its own. The same value could live in any of these tiers. This picture shows its possible locations, not a route it travels. 4 tiers stack from registers at the top down to global memory at the bottom. Right now, the value sits in a register at the top, its fastest possible home. It could also live in shared memory or L1, one step down. Or in L2 cache, another step down, dimmer because it is slower to reach. Or all the way down in global memory, the slowest tier of all. The lower the tier, the slower it is to reach. This is not a route it follows automatically. In a loop, a variable like float sum is likely to stay in a register the whole time. Reading an array element, like at index I, touches global memory on every single pass. Float sum sits in a register, likely on chip. That usually costs 0 memory operations inside the loop. At index I comes from global memory instead. That load may hit L1 or L2. If it misses both, it is a slow, off-chip read. Keep hot values in registers. A global load may hit L1 or L2, or go all the way off-chip. A kernel might declare a big, fixed-size local array, assuming it lives in the fast register file. A local array can outgrow the compiler's register budget. It can also get indexed with a runtime value the compiler cannot resolve. Either way, it spills to local memory, which physically lives in slow global DRAM, the dynamic memory out on the board off the chip. There is no error and no warning. Your on-chip array is now off-chip, and the kernel slows down. Let's recap. Memory is a hierarchy. Registers, then shared memory or L1, then L2, then global VRAM. Higher is faster with a narrower scope. Lower is slower with a wider scope. Shared memory is per block and you manage it. L1 is a per SRAM cache. They share one SRAM, but they are different tools. Now we turn to the most important factor for global memory speed. When a warps 32 threads read 32 neighboring addresses, the hardware serves them in just a few transactions. Scatter those same addresses, and it costs many more, and wastes most of the bytes it fetches. Global memory is read in fixed-size chunks. What a warp asks for all at once decides how many chunks that read costs. When a warps 32 lanes read 32 contiguous 4-byte words, the hardware folds them into just a few 32-byte sector transactions. That folding is called coalescing. A warp reads 32 neighboring words. Every lane points straight up to the word sitting right above it. At the top, 32 contiguous 4-byte words in global memory. Below, the warp's 32 lanes, lane 0 on the left, lane 31 on the right. Each lane connects straight up to its own aligned word, one lane, one word. We draw 11 of the 32 links, so the picture stays readable. Those reads fold into just a few full sector transactions. Every fetched byte gets used. 32 aligned reads fold into a few full sector transactions. Every fetched byte is used. Now the same 32 lanes read words that sit far apart from each other. The reads can no longer fold together. The same warp of 32 lanes is here. This time, each lane's target word is scattered across a wide range of memory. 8 of the 32 lanes are shown. Each lane now reaches far across memory for its own distant word. This is a genuinely far apart pattern, not a shuffle among neighbors. Each lane costs its own separate sector. The transactions are many and thin, and most of every fetched sector goes to waste. Far apart reads cannot fold. Each lane costs its own sector, and most of every fetched sector is thrown away. Picture a row major 2D array. Let thread index X pick the column, then adjacent lanes hit adjacent memory. One warp reads across row 0 of the matrix. 8 of its 32 lanes are shown, and thread index X is the column. Laid out in memory, row 0 forms one contiguous block. Adjacent lanes reach adjacent memory, so the reads coalesce. Row major layout, with thread index X on the column. Neighbors in the array are neighbors in memory. Keep the same row major array, but now let thread index X pick the row instead. The math looks symmetric. The memory pattern is not. One warp now reads down column 0 of the matrix. 4 of its 32 lanes are shown, and thread index X is the row. In memory, those column elements land one row width apart, at positions 0, 8, 16, 24. Big gaps sit between every touched cell. Thread index X walking down a column makes adjacent lanes red, addresses a whole row width apart. Coalescing is destroyed, even though the math looks symmetric. Let's recap. A warp's reads coalesce when they touch few 32-byte sectors. 32 contiguous words is the clean case, but a permuted or partly active read landing in those same few sectors also coalesces. Reads spread across many sectors cost many more transactions and waste most of every sector. So make thread index X walk across memory, the row, not down it, the column. Now we turn to shared memory, a small, fast scratchpad that lives right on the chip. You decide what goes into it, one block at a time. But the moment threads start cooperating through it, they need a barrier to stay in sync. Shared memory is a small, fast, on-chip region. It is private to a single block. Unlike a cache, you decide what goes into it. A block cooperatively loads a tile of data once, and every thread reuses it fast. But the moment threads cooperate, they need a barrier to stay coordinated. Every thread carries one value into the shared tile. A barrier holds all of them back until everyone has arrived. 8 threads, thread 0 through thread 7, sit at the top, each about to write into an 8-slot shared tile below. Every thread writes its own value into its own slot of the tile. A barrier gate holds everyone back. It waits until all 8 threads have written. Once every thread has written, the gate opens. Now the whole block reads the finished tile together. Write, then barrier, then read. The gate only opens once every thread has finished writing. That gate has a name, __sync threads. The cooperative load and a reversed read both fit in one small kernel. The kernel declares tile as ___ shared, an 8-float scratchpad for the block. Every thread writes tile at index T from the global input. Then __sync threads blocks until every write is done. The kernel reads tile at index 7-T, a slot that belongs to a different thread. That read only happens after the barrier. Reading tile at index 7-t is only safe because the barrier guarantees the whole tile is complete. Drop the __ sync threads call, and that reversed read becomes a race. Without the barrier, a thread may read tile at index 7-t too early. The thread that owns that slot may not have written it yet. Then it reads old, leftover, or garbage data. That is a data race. Now here is the trap. These 8 threads are lanes of 1 warp, so they step together, and this tiny kernel will often look correct even with the barrier removed. Running it and seeing the right answer proves nothing. Grow the block past 1 warp, or change your compiler or your GPU, and the wrong answer can show up at any time. The barrier is what makes the read correct by construction, instead of correct by luck. It is required, not optional. Let's recap. Shared memory is a small, fast, per-block scratchpad that you fill yourself. A block cooperatively loads a tile, then reuses it on chip. Cooperating safely means a barrier __ sync threads between everyone writing and everyone reading. Shared memory has a hidden cost. It is physically split into 32 banks. When 2 or more lanes want different addresses in the same bank, they serialize, one after another. Lanes reading the exact same word are the exception, a free broadcast. Shared memory is physically split into 32 banks. All 32 can be read at the same time, 1 bank per warp lane. Each bank is 4 bytes wide, and the word at index I lives in bank I modulo 32. Keep that rule in mind, because everything that follows depends on it. If each of the 32 lanes touches a different bank, all 32 accesses finish in 1 pass. That is the fast case. 32 lanes, 32 banks, 1 lane for each bank. Every access lands on its own different bank. The warp's 32 lanes sit at the top, over a row of 32 shared memory banks below. Each lane maps straight down to its own bank, 1-to-1. All 32 finish in a single pass. There is no bank conflict penalty. 1 lane per bank. The whole warp's shared reads finish in a single pass. Now change the stride, so the lanes read different words that all map to the same bank. Now they serialize. The same 32 lanes are here, but this time they all point down toward 1 shared bank. Every lane wants a different word, but all of those words sit in that 1 bank. Those 32 accesses cannot run together, so they serialize. 32 passes instead of 1. Different addresses in 1 bank cannot run together. The warp pays for 32 serial passes. One case looks like a conflict, but it is not, when all 32 lanes read the exact same word. All 32 lanes point toward 1 single word, sitting in 1 bank. Because it is the identical address, the hardware broadcasts that 1 value to every lane at once. There is no conflict. All lanes reading the same word is a broadcast. The hardware sends 1 value to every lane at once. That is not a conflict. Picture a square tile, 32 by 32 floats. A column access tile at row thread index X, column K, lands every single lane on the same bank. This is a pattern sketch, the index math only, not a runnable kernel. Each row of tile is exactly 32 floats wide, so word indexes 1 row apart differ by 32, and they land in the same bank. Reading column K puts every lane's word in that 1 bank, a 32-way conflict. Pad the declaration to 32 by 33 instead. Each row then shifts by 1 float, so the lanes spread across 32 distinct banks. Rows of exactly 32 floats make a column collide. Padding to 33 shifts each row by one bank, and the conflict is gone. Sizing a shared tiles row to a multiple of 32 feels like the natural choice, but that is exactly what makes a column access collide on one bank. The fix is the classic +1 padding trick, not a smaller tile. Let's recap. Shared memory has 32 banks. One lane per bank finishes in one pass, with no bank conflict penalty. 2 or more lanes reading different addresses in the same bank serialize. All lanes reading the same word is a broadcast, not a conflict, and +1 padding usually fixes a stride conflict. Now a different kind of memory. When every thread reads the same read-only value at the same time, constant memory can help. It broadcasts that value to the whole warp at once. Some data is read-only, and every thread wants the exact same value, like a filter coefficient or a physical constant. Constant memory is small, and it is cached. When every lane in a warp reads the same address, the hardware broadcasts that value to the warp. All 32 lanes get it at once. One address sits in the constant memory box. One value reaches all 32 lanes at once. At the top, the constant memory box holds C at index 0, a single value. That one value fans out along every line, down to every lane of the warp, all at the same time. One broadcast reaches every lane at once. A single value reaches all 32 lanes together. That is different from Coalescing's 32 separate parallel reads. A minimal coefficient example, not a full convolution. Every thread multiplies its own element by the same coefficient, C at index 0. The host fills __ constant float C, an array of 8, through CUDA mempy to symbol. Then every thread computes its global index. If that index is in range, it multiplies its own input by C at index 0. Constant memory is for warp uniform, read-only data. Texture and surface are separate memory spaces with 2D locality caching. They are named here, but this course does not cover them. Moving an array into constant memory does not guarantee a general speed win. It fails when threads read different addresses of it, like a per-thread lookup table. Constant memory only helps when the whole warp wants the same address at once. Divergent addresses serialize instead of helping. Let's recap. Constant memory is small, cached, and read-only. It broadcasts one value to a whole warp when every lane reads the same address. It is a broadcast, not a cache for any read-only data. Divergent addresses serialize. Now we turn to the labs. Predict which pattern wins. Coalesced against strided, conflict-free against conflicted. The schematic bar chart shows which one wins. In code, you measure it with the CUDA event timing technique from part 3.6. The pyramid says where data lives. Coalescing helps global memory reads reach their promised bandwidth. Conflict-free access does the same for shared memory. On the left, the pyramid at rest. On the right, 2 schematic bar groups, each on its own baseline, one for global memory, one for shared memory. There are no numbers here. The strided bar and the conflict bar both stand short. Compare bars only inside their own group because shared memory is far faster than global memory. Fix the access pattern to coalesced, and in the global memory group, a tall bar grows right beside the strided one. Pad the tile, and in the shared memory group, A tall padded bar grows beside the conflict 1-2. Higher is better inside a group. The good access pattern grows the bar toward the bandwidth that tier promises. The two groups are not compared with each other. Lab 1. A warps 32 lanes each read at index thread index X from a plain 1D array. Predict first, what address does lane 0 read? Lane 1, lane 2. Are those addresses neighbors or far apart, so does the warp coalesce? Lane K reads at index K, so neighboring lanes read neighboring words. That is coalesced, a few transactions and no wasted bytes. Predict on paper here. In real code, you would measure each pattern with the CUDA event timing technique from part 3.6. Lab 2. A warp reads tile at row thread index X column 0 from a shared tile of 32 by 32 floats. Predict first. Each row is exactly 32 floats wide. Which bank does tile at 0, 0 land on? Tile at 1, 0. Tile at 2, 0. Are those the same bank or different banks? What one character change would spread them out? It is a 32-way conflict. Rows of 32 floats put every column 0 element on the same bank. Padding the declaration to 32 by 33 fixes it. Computing achieved bandwidth from only the bytes you read forgets that a full round trip also writes an output. That undercounts the total bytes moved, and makes an already fast coalesced kernel look artificially slower than it really is. First, most kernels are memory bound. The goal is moving less data faster. Second, know your tier. Registers, then shared memory or L1, then L2, then global VRAM. Third, coalesce your global reads. Make thread index X walk across memory, not down it. Fourth, shared memory plus the barrier. A cooperative tile load, then __ sync threads. And fifth, avoid bank conflicts and broadcast your constants. One lane per bank and a same address broadcast.